Alright, let's go through the normal approximation to the binomial. So basically the normal approximation to the binomial is when you take the continuous distribution, which is the normal distribution, and you want to approximate a discrete distribution, which is the binomial distribution. Basically saying that the normal distribution can be used as an approximation to the binomial distribution, and under certain circumstances we're saying, given that if you have a random variable x which follows the binomial distribution np, and n is large and p is close to half, then we're saying x can be approximately normal. So given a binomial distribution, we can use the normal distribution to find the answer for that. In this example, we're told that a fair coin is tossed 888 times. Find, by use of a suitable approximation, the probability that the coin lands heads up at most 450 times. Alright, so a fair coin is tossed 888 times. So we're looking at a discrete distribution. So we're saying that we've got some random variable which is following the binomial distribution, where n is equal to 888. That's the total number of times n. And p is going to be, it says the probability the coin lands heads up is 450 times. So what is the probability that a coin would land on anything at any point in time? We know it's equal to half. Right, so let's say 0.5 or 1/2. So there's my n and there's my p. Remember, that's your binomial distribution. So we're letting x represent the number of times the coin lands up, given n is equal to 8. Now, we're not using the binomial distribution to solve this, we're using a normal distribution to solve this. So when we use a normal distribution to solve this, we start approximating it using the formulas n times p to get the mean, and n times p times q to get the variance. Alright, so we've got to make sure that we put this in here and create from the binomial the normal distribution. So here we go. This is going to be now a normal distribution. So we're going to find that n times p is going to be equal to 888 times 0.5, which is equal to 444, and that's going to be going in here. Okay, so remember that's np. Then we've got npq, which is equal to 222, because we would take that and multiply it by half again. So we get 222 to be npq. So that takes us to our variance and our mean. And just like any other ordinary day where we have the normal distribution with our mean and our variance, we can then use or standardize it by taking z is equal to x minus mu, using our coding for z, for sigma. And just remember, this is sigma squared, so we have to square root it to get it into the formula. Now the probability in this case, they want to know that the coin lands at most 450 times. So what does it most mean? That's another important concept. It means that it must be less than or equal to 450. So the probability that the random variable x is less than or equal to 450 is equal to the probability. Now we have to use coding. Remember, this is part of the original normal distribution. We have 450. We want to convert it into the standard normal with a mean of 0. So the z value needs to be calculated using this formula over here. And so we calculate the z value now with our x being 450 and minus our mean, which is 444. Okay, remember that is 444, and our standard deviation is the square root of the variance, which is 222 in this case. Alright, calculated over there, I just rewrote it over there. Now, the one thing you notice about this is that in order to ensure that the probability of x is less than or equal to 450, we have to use 450.5. Alright, we have to use 450.5. We call this the continuity correction. So to ensure that the probability is less than or equal to 450, we're going to use 450.5 as the continuity correction. Alright, so it's about replacing a number by moving half a decimal down or half a decimal up, depending whether you are including the number or excluding the number, and also in context with the question. We then calculate this probability after finding our z value, and this comes to 0.436. So remember, there's a continuity correction there. I'm going to put there CC, and we got 0.436. So we put 0.436 into our tables, and when this goes into our tables, we then end up, so 0.436, we end up with the probability being, using our z tables, 0.6686. So therefore, the probability that at most 450 heads would be equal to 0.3 significant figures 669. That's my final answer. The concept of a continuity correction is basically, remember, we're dealing with a discrete distribution. So when we approximate the discrete distribution by a continuous distribution, we're saying that the discrete value must be treated as being represented by a class of a continuous values. So if you got a solid value like 450, remember, in the continuous space you include all decimals in between, and it's for this reason we replace 450 with 450.5. Okay, if you want to summarize it, the whole idea behind this is that if we had, for instance, probability x was less than 450, then our calculator would change. So this is just to show you the idea of continuity. Now remember, this is strictly less than. So when you have strictly less than, that means you can't go over, right? You can't go over, which means it excludes the 450. So therefore, your z coding to get your z value will be 449.5, because we're minusing off a decimal in the discrete space, accounting for the discrete space in the continuous space, or vice versa. You can look at it like that, and you can see this is 450.5, this is 449.5 now, over the square root of 222. So what is the deciding factor for whether you plus or minus when it comes to continuity corrections? When you have less than, you notice that you are going to minus 0.5 when you're approximating to the binomial, and if it's less than or equal to, you are going to add 0.5 to include it. If you look at it in terms of greater than, the probability that x is greater than a number, then you would, in this instance, add 0. Because it must be more. So you would add 0.5. And if it's greater than or equal to, that means that you have to make sure that it is including the number, and in this case you would minus 0.5. So if it's greater than or equal to, then you would minus 0.5. Okay, that's a hypothetical example of scenarios of how you would calculate it.